Believe it or not, the first hydrogen engines were actually developed in the 1820s, and it was a bit of a weird one, didn't really catch on, and it wasn't until 60 years later when our main man, Dr. Otto, I don't know if he was a doctor yet, but Otto, creator of the Otto cycle, actually started experimenting with fuels with a gas mixture in them, and mostly which was hydrogen, right? He experimented a bit with gasoline, and believe it or not, he went backwards and said gasoline was too dangerous, so he went back to his hydrogen, and a little bit later, carburetors were invented, and we sort of went over to the modern combustion engine that we use gasoline and diesel in today. But could there be a resurgence? Could we be looking at hydrogen combustion engines in 2025? We're in 2025. Can you believe it? Hydrogen is, as we know, the fuel of choice for space. It's taken us to places like the moon and maybe to Mars. But will we, like I said, see a resurgence in hydrogen engines in the modern day? Guys, you are with us again for the High Level Podcast. Thank you for joining us. My name is Jonathan, your host, and I'm joined as always by my beautiful co-host, Mr. Damon Hunselaar. How are you today, kind sir?
Hello there.
That was very nice, talking to the camera. I love it. How are you doing, Mr. Hunselaar?
I'm doing fantastic.
You've had a few math problems today.
Yeah. Let's not ruin the mood. Yeah.
Surviving there. All right, guys, so we are talking hydrogen vehicles today. Is hydrogen combustion specifically going to be an engine we might consider in the future? So, Mr. Hunselaar, I have some stats for you. Just to open up the conversation, Let's talk about combustion engines.
Sure.
For those of us that don't know, most of the cars sold in the world are combustion engines, right? The normal car that you probably are driving to work is a petrol-powered car or a diesel-powered car. That's what we class as a combustion engine. And about 59 million new ICE vehicles are sold every year. That's not even the second-hand market or anything. So close to 60 million ICE vehicles. And in 2023, we saw about 14 million battery electric vehicles. So things like your Teslas, what other electric cars are there? I feel like there's more. BYDs, things like that. Anyway, fully electric cars. So they're gaining a lot of market share. 1 in 5 cars in 2023 sold was a battery electric vehicle.
Sure. I didn't know it was that.
Yeah, it's a lot, eh? It's really catching wind. I don't want to say catching wind, catching electricity. Right? Hey? And now we get to the sad one, sort of a rounding error in the whole car picture. About 14,500 hydrogen cars. Now, of that figure, I don't know what would be hydrogen combustion, but of the 14,500, which is already a rounding error, a rounding error of that would be combustion vehicles. Pretty much 99% of all the hydrogen-specific vehicles in the world that are sold will be a hydrogen fuel cell, not hydrogen combustion. But today, we want to talk about hydrogen combustion. So taking your normal petrol or diesel engine, converting it over to use hydrogen gas or hydrogen liquid as the combusting fuel to drive you towards your dreams. Okay, so why do we want to discuss that, Mr. Hunselaar? Well, I've got some efficiencies here for you. This is going to come down to efficiency and a bit of economies of scale. So do you know the normal range of efficiency for a normal ICE vehicle?
For a normal range of efficiency?
Yeah. What do you think the efficiency is from where you pump your petrol to where it goes onto the road?
30%?
Pretty much. So most gasoline vehicles, and I don't actually know, like wherever you get efficiencies from, I've got it between 11 and 27% efficiency, but this is from well to wheel. So they go all the way from the oil well to where it actually gets.
So we're looking
to
at the bigger
wheel.
picture. Yeah,
The bigger picture.
we're not looking at your engine efficiency. We're looking at the value chain efficiency.
The whole value chain incorporated, about 11 to 27% of the energy in the fuel is getting you to move forward. Okay, so that's normal. ICE vehicles, diesel engines range from about 25 to 37%. Then I got your compressed natural gas, 12 to 22%. I think that would be more like larger scale transport, things like that. I know a few forklifts work on that as well. But if you're just looking at the conversion efficiency, so a liter of petrol, how much of that when you combust it is actual usable energy that drives the shaft or whatever? Usually between 20 and 40%. And a lot of the guys are driving towards like the 50% mark for combustion efficiency. Now, if we look...
Okay, so there are we talking about...
That's specifically...
The engine itself.
The engine itself. So no rolling friction, nothing like that. Nothing about the process to get the gasoline to the petrol station. Nothing like that. Just the engine itself.
Okay.
So between 20 and 40%. And lots of guys driving for 50%. If we look at hydrogen fuel cell vehicles, so this is from hydrogen to the end product, between 40 and 60% in a fuel cell. And then if we look at battery electric vehicles, so EVs, there's a big range here, but if you do from well to wheel, which there's no real well with
from mine to
with electricity, depending on where you get the electricity from. I found this study they did from, so if it's from coal, you're looking at between 13 and 27%. And if it's from a diesel generator, between 12 and 25%.
Okay.
And then if we look at now, obviously EVs, we want to drive towards renewable energies. You can get anywhere upwards of 40% up to about 70% efficiency, depending on where the renewable's coming from.
Yeah, I mean, I guess it really depends on, like you said, where is the energy coming from?
Exactly. How efficient
if it's a solar cell, is it a power plant that runs coal?
Exactly. So there's a wide range here, and the reason I want to open with this is just to show you guys, because we're going to come back to this at the end, where the efficiencies of normal ICE vehicles are currently, and if moving over to just hydrogen combustion is actually worth it at the end of the day. So remember the big ones to remember, fuel cells, between 40 and 60%, because that's going to be the big one we gauge against. Is it worth it to just combust the hydrogen right there and then? Or is it rather worth it to put it through a fuel cell, make electricity to drive an electric motor?
These are the important questions.
These are the important questions. So guys, for today, we're going to introduce you guys to hydrogen we're going to call it H2 ICE, H2, hydrogen internal combustion engine, versus a normal petrol engine or a diesel engine. That's the main comparison we're going to be making, and we'll talk a bit about that towards the end. But there's a few metrics that we're going to go through here to sort of rate hydrogen as the source of fuel that you're going to use to drive your engine. And the first one we're going to look at, there's 7 in total, so we're going to rank them. I have my handy notebook. We're going to decide, does gasoline win in this one, or does hydrogen win in this one? And at the end, we'll give it a score. How does that sound to you, Mr. Unselaar?
Sounds fun.
Sounds like fun.
Yeah.
Sounds like fun. All right. With that being said, let's get into number 1. So one of the big what's the advantages of hydrogen is that, believe it or not, it has a very wide range of flammability. Now, this plays into a bigger sort of picture in terms of air-fuel mixture. So if you've ever been into engines or anything like that, you'll know that the air-fuel mixture in an engine is very important, and there's a few metrics we're going to throw around here. So the first thing I want to introduce you guys to is what's called the stoichiometric, or the theoretical air-fuel mixture that's the best for combustion. And this you work out with a chemical formula. For hydrogen, it's about 34 to 1. So in other words, about 34 parts of air to 1 part of hydrogen is the best fuel mixture. It's where you'll get total combustion.
Is that in mass or is that in volume?
That would be in mass. All right, so 34 parts of air to 1 part of hydrogen. In terms of mass, you'll get full combustion. It will be the most efficient, but we live in the real world, and sometimes that's not really the best way to go about this. So you have stoichiometric or theoretical air fuel mixture, and then you have on both ends of the spectrum, you can run a lean fuel mixture, as in less fuel to air, or you can run a rich fuel mixture. So for guys who are familiar with engines, this will be a very normal thing for you. But a lean fuel mixture is where you run less fuel to air. And this, in general, rule of thumb, is where you're running more economically. So in petrol engines, your stoichiometric efficiency, or your air fuel mixture, is 14.7 to 1. Most car manufacturers will be aiming for that range. If you want to run a lean fuel mixture, you'll see that little graph I have on the next page there. The lean fuel mixture, you'll go pretty close to about 17 to 18 to 1, and that's the leanest you're going to get with a normal combustion engine gasoline. If you're going to run a rich fuel mixture, which means there's more fuel per unit of air, you're going to run down to about 12 units of air to 1 unit of gasoline. And in that case, you get a bit more power, and then it tapers off towards the end, because as you add more fuel to the mixture, not all of it will combust because there's not enough air to combust with. So that's the general rule of thumb. A richer fuel mixture, up to a point, you get more power. A leaner fuel mixture, up to a point, you get more economy. So the interesting thing about hydrogen is you can run very, very, very lean amounts of fuel, up to about 180 parts air to 1 part of hydrogen. The trade-off is you get less power, obviously, but you're running more economically. So it's got a pretty wide range of flammability, which we're going to say in this case, unless you have anything to add to that, the leanness that you can run hydrogen is a very good thing, and it outperforms petrol because it has such a wide range of flammability. I'm going to give this point to hydrogen in internal combustion engines. Are you with me on that?
I'm with you on that. It's very clear that, just in terms of economy,
right?
And also, like, judging by this little diagram you've got here, it also looks like you can also run it with quite a rich mixture as well. So like if you want more power, you can get more power. So it's, to me, that it seems also very customizable.
Yeah, you can play around
so
with it.
Yeah, I would agree with you. This point goes to hydrogen.
Goes to hydrogen, right? So you can basically use less fuel in more air and get more complete combustion, get better economy if economy is what you're looking for. So first point in terms of hydrogen having a very wide flammability range, that goes to hydrogen. Sorry, gasoline, you lose out on this one. Now, Mr. Unselot, point number 2, you're going to take us through there.
Yeah, so the next point that we're going to discuss is that hydrogen has very low ignition energy, and it's about an order of magnitude lower than that of like gasoline or diesel. So yeah, I'm sure you're going to throw up this graph here as well.
100%.
So you'll see on the right there's the red graph, and you can see that it is like divided by 10. So if you take the one on the right, divide by 10, then there we go. So that's what we mean by when we say an order of magnitude. So essentially what that means is for us to trigger the combustion reaction, it takes a lot less energy to get hydrogen to combust. And again, that's why we say hydrogen is so combustible, it's so volatile, because it doesn't take a lot to get it to start. So this is partly why, to go back to your point, why you can ignite lean mixtures. But there is a bit of a downside to it. Because of this low ignition energy, it means that hot gases and hot spots on the cylinder can serve as a source of ignition, and that can create premature ignition and flashback, which can be a problem. So preventing this is one of the challenges associated with running a hydrogen engine. And yeah, so the wide flammability range of hydrogen means that almost any mixture can be ignited by a hotspot. So yeah, for this one, I don't know. I would say this one's a bit of a 50-50 because while it's very volatile, that can make it a bit more dangerous. I don't know if you have anything to add.
I would say the low ignition energy is one for gasoline. So I think the only thing you get out of this is you can use a lower energy spark plug. But the fact that if there's hot spots in the cylinder, you're going to have that downside of maybe you have ignition when you don't want ignition.
Exactly.
So you might have some knock in the engine, mistiming, things like that. So I think it sounds like a good thing, like on the face of it, if you don't understand how the engine's functioning. But the fact that it has such low ignition energy means you might have misfirings. So I'm going to give this one to gasoline. I don't know if you feel the same.
Yeah, I think let's give this one to gasoline.
We're giving this one to gasoline. So the low ignition temperature of hydrogen sounds good on the surface, but not the greatest, right? Not the greatest for that. Okay, so 1 to gasoline. All right, guys, it's head-to-head now. We're about 1-1. Moving on to point number 3, the quenching distance. Now, for those who don't know about the quenching distance, because I did not know about quenching distance before this episode. So quenching distance is basically the boundary layer between two parallel plates. And in our case, it would be a cylinder, so the edges of the cylinder. As the flame of something, a fuel that's ignited, as it travels towards the boundary, it gets quenched. That's basically the term. But basically, you get a lot of thermal transfer at the wall, and different fuels quench at a different distance away from the wall. That's basically the story. Now, hydrogen has a very, very small quenching distance. You'll see I put in a nice table there. Your quenching distance in millimeters at the perfect air-fuel ratio now is 0.64 millimeters. Very, very small compared to C3H8. I think that's propane, right? And that's at about 2 millimeters. And I think gasoline is even larger than that. So the real reason why quenching distance is important is because at that wall, sometimes if you don't have a valve closing correctly or quick enough, you'll get basically the flame travel back into where the injection is happening in the fuel line. So you get flashback back into the injection line of the fuel. So quenching distance is sort of a balancing act, but the fact that hydrogen has such a small quenching distance, not a good thing for us when we're designing engines or anything like that. It's not going to be great. It does mean that the flame combusts more completely around the cylinder. So you get like more uniform sort of heat transfer. But I'd say in this case, not a good thing for engines if we want to outfit them at the moment. Like just take a petrol engine, outfit it for hydrogen. I'm going to say not a good thing. What's your view?
So clarifying question.
Go for it.
So the smaller the quenching distance,
the closer to the
if
wall.
I can really simplify it, does that mean that the flame is basically closer to the wall?
The flame extinguishes closer to the wall.
Closer to the wall. So I would say that increases thermal transfer. So you would transfer more energy to the walls.
It depends on the fuel. I wouldn't say it increases fuel. It's like, I think I hear what you're saying. So there's a greater heat transfer at the boundary, basically.
Yeah.
Yes, yeah. And it's closer.
And do you think that would cause any like thermal stresses or thermal fatigue on the engine wall?
I think that depends more on the actual ignition temperature, to be honest with you. I don't think it matters with the flame, because you could have a low burning flame.
So when we're talking about quenching distance, we are more worried about the flame traveling to unwanted areas.
Yeah, so that's basically because obviously engines, because remember guys, the big goal here is to use existing infrastructure. So to use an existing combustion engine, make as few changes as possible to use hydrogen. Now, these things are made for petrol that has a larger quenching distance. So if you decrease that quenching distance, you might have it that combustion has happened and the valve hasn't closed completely. And because that quenching distance is so small, now the flame can get into the actual line where fuel is. So that's the whole risk around.
So then I would say if we had to consider all of these, I think the point goes to
gasoline, right?
What are we going to call it? Fossil fuels.
Fossil fuels. We're going to say
fossil fuels.
Fossil fuels. Okay, sweet. So that's point number 3, the quenching distance of hydrogen being very, very, very small.
All right. Cool. So point number 4 that is important is that hydrogen has a higher auto ignition temperature. And what this essentially means is that...
Tell me what it means.
If the hydrogen gets hotter, then there'll be a point where you get, it ignites itself. I think a lot of the time we call it the flash point.
Yeah.
Correct me if I'm wrong.
I would say so.
Hydrogen is sitting at about 585 degrees Celsius. And if we have to compare that to petrol or diesel, we're looking at about 210 degrees Celsius to about 480 degrees Celsius. So, that auto ignition temperature is a lot higher for hydrogen. So what does that mean? It means, I would say this is a good thing for hydrogen, because it means we can actually compress the hydrogen more. Because very quick physics lesson. If you compress a gas very quickly, it's going to become hot. So your auto ignition kind of limits how much you can compress it, because if you compress it too much, it's going to auto ignite. So you might not want that. But because hydrogen has such a high auto ignition temperature, you can compress it more.
And more quickly.
Yeah, and more quickly. So, I mean, this is the reason why a diesel engine doesn't need spark plugs.
Spark clubs. Are the guys going in with clubs there too?
Yeah. Versus why a petrol engine needs spark plugs, because you can compress it and then you need something to ignite it. But with diesel, you can compress it and it will ignite itself.
100%.
I'm simplifying things.
No, fair. So basically, we can get higher compression ratios, which means higher efficiencies.
Exactly.
Compared to if we had just a normal gas.
And also, if you look at the Carnot cycle, quick thermodynamics lesson, the Carnot cycle is something that describes the maximum efficiency of any thermal cycle. Okay, and combustion is a classic thermal cycle. And if you can increase the range of temperatures, you can increase the efficiency of your engine. So that's another plus for hydrogen. So yeah, if I'm looking at these things, I'm giving this one to hydrogen.
I would too. I think also another thing that adds to the hydrogen story is that because the auto ignition is higher, you have more control. You won't have accidental ignition, basically. So you have more control over when the gas ignites, because you have a larger temperature range to play with. So yeah, I'm giving it to hydrogen. You happy to give it to hydrogen?
I think this one's unanimous.
Okay, sweet. Can I quickly fact check you? Are you ready to be corrected on camera? Is that all right with you?
Yeah, no. I'm here to learn.
It was an innocent mistake. Okay, so auto ignition versus flashpoint. Did a quick Google.
Okay,
right?
Cool.
So auto ignition is the temperature at which a substance will spontaneously ignite without an external ignition source.
Okay.
But a flashpoint is the temperature at which liquid produces enough vapor to ignite when exposed to an ignition source. So flashpoint needs an ignition source. Auto ignition needs no ignition source.
Learn something new every day.
Sorry to embarrass you in front of your friends there, Brie.
It's all right.
All right, guys. Moving on to point number 5. We're really motoring through these. Something for the boys. High flame speed.
Oh,
right?
yes.
Yeah, all
I like
for
the
the
sound
boys.
of that.
Right? We all love setting things on fire. That's
exactly.
basically it.
I think it's something primal.
It must be, It's
like when you're having a braai at home and you just see that fire burn, you feel like a man.
100%. And if there's a piece of paper, I'm lighting that thing on fire, man. Piece of wood laying around, a piece of pallet, I'm lighting that thing on fire. 100%. But anyway, so if we're comparing flame speeds now between gasoline and hydrogen, so flame speed is exactly what it sounds like. How quickly the flame travels. And it's in laminar flow. We're not getting into turbulent flows here. We're going to simplify things a bit here. Okay. So there's no turbulence here. But they measure these under laminar conditions, which means there's no funny things going on. It's fairly straightforward flows. In general, hydrogen as a flame travels faster than a gasoline flame. And quite a bit. If you look there, I gave these little charts here. So they measure it in centimeters per second. You'll see hydrogen there. If you look at it, it's on that first graph in that black curve. We're at about 3, would you agree with me, about 250 to 300 centimeters per second?
For hydrogen?
Yeah, that black line.
Yeah, I know.
Right?
That's
250 to 300 centimeters
fast
a second.
boy.
That's fast, boy. That's fast. And then if you look, the one on the right there is gasoline. You're there at about 50 centimeters a second. So 5 to 6 times the speed of a gasoline flame. Now,
okay.
Yes,
so just to clarify, is that if I say I have a hydrogen mixture, and then on the left I light the flame, and another mixture is igniting, because obviously it propagates from the source point, and then it's how fast that is traveling.
100%.
Okay.
So if you had a horse race of gasoline next to hydrogen and you lit them both at the same time, hydrogen would travel 5 to 6 times faster.
And then I'm seeing that if you have a higher concentration of hydrogen, that the flame gets faster to a point, and then it actually starts getting slow. I'm assuming that is because it's overly rich, so there's not enough oxygen for it to ignite. That could be the reason.
Could be. So that phi that you see, I didn't know if we were going to get into this or not. But phi basically tells you when they do the measurements in the lab, what's the actual fuel mixture over the stoichiometric fuel mixture. So if you run richer fuels, your fraction will be over 1. If you run leaner fuels, it will be under 1, right? So that's phi, basically. So phi, like you say, up to a point as you run richer mixtures, and then it starts to drop off because there's just too much fuel in the air, basically, to get through. But the real question becomes here, we can see clearly that the hydrogen flame travels quicker than the gasoline flame.
Yeah.
Is that a good thing or a bad thing for engine efficiency? That's the question. Don't look at the answers. What would you say? Or have you already looked at the answers?
I haven't looked at the answers, but
Okay.
I would say it's a good thing, because then you can have complete combustion.
Very nice.
And your engine can run faster.
Very nice. So you get faster combustion, agreed. So things happen more quickly throughout the combustion chamber, and it's more likely that you get complete combustion. 100%. This is why you have a master's degree, Mr. Hunselaar, because you think like this. You know what I mean? Bar your maths problems.
Yeah.
Bar the maths problems. But you'll also reduce the tendency to knock in an engine because you have such a fast-moving flame. There's no chance for the knock, and you have better fuel utilization. Again, I think that just comes back to you get complete combustion in the chamber. So this means that because the flame is acting so much more quicker, you get a lot closer to the theoretical efficiency of an engine because you're having that more complete combustion. So I think we're going to give this one pretty handily to hydrogen.
Yeah.
Right? No problem
What's
there.
the score now?
What's the score? We're at 3-2.
3-2.
Did I
No, gasoline can still take it. We've still got 2 things to discuss.
Okay, fair enough.
Okay, so the next thing we're going to discuss is
Go for it.
high diffusivity. Diffusivity.
Yes.
So essentially, hydrogen has a very high diffusivity. So what that means is, if I have a really high concentration of hydrogen, and I'm waiting for it to mix, it's basically a measure of how long does it take for it to mix in a container. So so I'm sure you can imagine why that's a good thing.
Yeah, it's like if you fart on the one side of the room.
How quickly does the other oak on the other side smell it?
There we go. All right, yes.
Yeah, so essentially what this means is that it facilitates the formation of a uniform mixture of the fuel in the air. Again,
Better
that's
combustion.
better combustion.
100%.
And also, if, say, there's a hydrogen leak, that hydrogen is going to want to spread very quickly, which decreases the risk of problems. You know what I'm saying?
Yeah, 100%. I think that also came out from when we had the interview with Matt.
Yeah.
Basically, that gasoline, if there's a leak, will just sort of stay on the floor until you drop your cigarette, and then you're in trouble. But hydrogen will sort of rise and disperse away. Unless you're in an enclosed room, then it's a problem. Maybe.
Yeah. So I guess it's very much a situational thing. But if we're talking about efficiency, the diffusivity is a good thing. Also, to go back to the previous point, you get more complete combustion.
100%.
So I think
if we're going for efficiency, it makes a lot of sense. So, what's your verdict?
I would say we're giving this one to hydrogen.
Giving this to hydrogen. That's a 4.
It's a close one. I'll say that much.
Hydrogen's won already, man, because it's only 7 points and it's at 4. So it's 4-2. Let's see what the last point is here. So we've got the common objection to hydrogen. I feel like this is what our lives are all about. The low density of hydrogen.
Exactly.
Actually a real bitch to deal with. But hydrogen is very low density, very low volumetric density. It's the most energy dense atom in the universe, but it's a bitch to try and store and use. Basically the story of hydrogen's life. Two big problems with that. If you want to store hydrogen, obviously in tanks in your vehicle, you have to compress it a lot, and the tanks take up a ton of space. So it takes up a lot of space, very low density, and because it's low density, volumetrically, you're going to have a very low energy density that you can store. The common problem with hydrogen, don't want to harp on about it, but we know about this. This is a common hydrogen objection. We're not giving this to hydrogen, right?
Oh, not a fuck.
Not a I think the other thing this comes into as well is because hydrogen's so hard to store, the containers you keep it in have to be so high tech versus a gasoline engine. You can put it in a plastic tin and it will be fine. So we're giving that one to gasoline. Pretty handily. And Mr. Hunselaar, final countdown. Hydrogen won this. Clearly won this.
So, but we clearly they can't be all good because we don't have that many hydrogen combustion engines around. One thing I've seen though is that like a common argument is that hydrogen is cleaner because when you combust hydrogen you get how true is this?
Well, I think even like if you're someone that clicked on this video now, you saw a hydrogen combustion engine, most likely you've got this idea of this is a cleaner fuel to burn because we want to move towards a better world, and a world where we all love each other and there's peace and less pollution, right? So in a hydrogen fuel cell, yes, this makes complete sense. In a hydrogen fuel cell, you are combining hydrogen and oxygen and you're getting out water. Excellent, great stuff, no problems there. Very smooth chemical reaction. In the case of a hydrogen combustion engine though, I think the thing to remember is we're drawing air into the engine, normal air that you breathe outside. And air only contains about 21% oxygen. A lot of the rest of it is nitrogen. I think it's 78%
close
or
to
something.
70.
Right?
Yeah,
70 something percent of that air is nitrogen. So this is where we get into a bit of the niggles of a hydrogen combustion engine. Don't get me wrong, it's cleaner than burning gasoline. We're not here to say it's not, okay? But the nitrogen in the air, because the temperatures get high in an engine, will combine with the oxygen and produce nitrogen oxides, which are bad for humans' health, bad for the environment, all of those fancy things. So it's not the cleanest burning fuel. I don't know if there's other cleaner burning fuels, but it's not a great fuel to burn specifically. It would be better to use it in a fuel cell. And you'll see those little graphies I put there right at the bottom of that page.
Yeah, it really looks like, if I'm looking at these graphs, when you look at hydrogen,
more or less the same
amount of NOx.
Right? So nitrogen oxide emissions, very similar to a gasoline engine, because gasoline's doing the same thing. It's burning a hydrocarbon chain, and some of the nitrogen and the oxygen is going to combine just due to the temperature and the pressure in the engine. I mean, you can't get away from that. What you do get away from, however, is the CO2 emissions and some of the hydrocarbon emissions. Obviously, you don't get into those types of things. So it is better to burn hydrogen in general than it is to burn gasoline. We're not saying it's not.
Fair enough.
But you don't get away from all the emissions, I think is what we're trying to say here.
Yeah.
Right? Do you agree with that, Mr.
I agree. I think it's good to look at the facts.
100%. So here we come back to wrap this all up in a nice little bow for you guys to take to your classmates and to impress them at the bar. Why do we not see more hydrogen combustion engines? I think we've given a very compelling case here. There's the infrastructure's there already. There's many car manufacturers that know how to build good engines. And it doesn't seem like it takes a lot to retrofit it to be a hydrogen engine. So, Mr. Hunselaar, why would you say that we're not getting to hydrogen combustion in 2025? I did ask you a question.
I would say, okay, this is purely
pure speculation.
Pure speculation. I would say one, hydrogen it probably doesn't have the best reputation in terms of combustion because of how volatile it is.
Yeah.
Also, the industry has been developed for diesel, and all the infrastructure is there for diesel and fossil fuels. And as we've discussed now, the points that were given to gasoline were pretty big points.
Yeah.
Like it won if you look at it in terms of 4 out of 3 or 4 out of...
Yeah, it was pretty close.
It was pretty close, but those 2 or 3 points that lost, They were big things. They weren't.
Yeah, I mean, like to put a tank in a vehicle that takes up the entire space of what a person would take up, it's a little bit to ask.
Yeah.
It's not a. Yeah. So I agree with you. So I'm going to give you some numbers here. So this is from a study, take a grain of salt. They estimate that about 40 hydrogen combustion engines will be sold in the world in 2025. And that's going to be into India. It's some partnership with Tata and some Ashok Leyland, whatever the story is. Whether those 40 get sold, I don't know. Yes, no, maybe. And they predict that about 10,000 H2 ICE vehicles will be sold in the year 2030, which is 5 years away. So it could happen. I'm not saying it won't happen. Could happen. It's predicted that 20 million trucks, though, will be sold in 2030. 20 million. And we estimated about 10,000 trucks in 2030. So for this, it really seems like a rounding error. To sell 10,000 hydrogen trucks is not going to do anything to anyone, if those even get sold. So the real question becomes, if the market doesn't want it, is it worth it? All right, so let's look at a few of the advantages of hydrogen, and there's not many. I think we'll say these just to get them out the way. Basically, if you're a country that is worried about your energy independence, so if you're not an oil producer and you want to get away from that, maybe look at hydrogen. But it doesn't mean you have to look at hydrogen combustion. You could look at hydrogen fuel cells as well. But this is more a general point. Maybe look at hydrogen as a fuel if you're not an oil producer and you're subject to that. The other thing to look at is that hydrogen engines are very similar to what a normal diesel engine is. It's seems, I'm not an expert, seems like an easy way to retrofit a diesel engine and you can start using hydrogen in it. No problems. The disadvantages, however, are where we get out the way.
Where we fall off the wagon.
H2 ICE is more expensive to maintain than a battery electric vehicle.
Always comes back to money, eh?
Always comes back to money. So it's more expensive over the lifetime to maintain it. And that's not even counting the fuel, because hydrogen is expensive itself, because the infrastructure is not built out. Which brings us to another one. The infrastructure for hydrogen is not built out. So why would you go for it if you're a big company now to retrofit your fleet? The other thing is, it doesn't offer enough. So let's say on the face of it, let's say we have all the infrastructure there. On the face of it, it doesn't make sense to retrofit diesel because it doesn't produce enough good benefits to outweigh the bad things of it. So you're actually paying for the privilege of running a hydrogen fleet, and you still have the emissions. You still have tanks taking up huge amounts of space. It doesn't really make economical sense. The other thing, I think the biggest thing for us as engineers, we've talked about the money now, is just the efficiency. So a fuel cell electric vehicle. So this is the question now, bigger picture. Why would you choose hydrogen combustion over a fuel cell vehicle? Fuel cell vehicle, 40 to 60% efficiency. A hydrogen vehicle is going to take on about the same efficiency as a gasoline engine, which, what did I say there?
About
the
30%.
first one was, let's call it 30%. Let's round to 30%. So you're really playing a game of low efficiency, not using hydrogen as best as you can, rather go the fuel cell route. That's basically the disadvantages of hydrogen. I hand it over to you, Mr. Unselar. Are you convinced about hydrogen as combustion, using in combustion engines?
Yeah, like we said, the bad outweighs the good,
Yeah.
even like though we scored it in that way. And again, I think the industry is moving more towards the fuel cell route again because efficiency. So yeah, it really seems like, I think maybe to answer the question plainly, why don't we have more hydrogen combustion engines? It's because we have fuel cells and they're a lot more efficient.
That's it.